All right. Thank you, Stan. So thank you all for being here. I really appreciate it. It's my honor to talk to you. I have to introduce a really broad field and also show you my one little contribution to that area. And so it's a really exciting opportunity for me. Star formation is my main gig. When people ask me, what do you do? I say I study star formation in galaxies. And I'm an observer. I use telescopes like the ones that are running on the banner here. And, but I don't concentrate on one area of the spectrum. I look at the entire spectrum, and particularly the two ends of the spectrum, if you will. Now, when we're talking about star formation, I'm kind of trapped here by the projector, but when we're talking about star formation, what we're mainly concerned with are massive stars. These are stars that are not like the sun. They're 3, 4, 10, 30 times the mass of our star. And why they're interesting is because their birth and their death are essentially instantaneous. Okay? I know that might sound kind of crazy, but because of that, they trace active star formation. Wherever you see a massive star, there are stars forming. There are no old massive stars. Massive stars are born and die really fast. It's like less than 10 million years. Okay, now again, that might sound strange, but I'm an astronomer, okay? So consider our sun's lifespan will be about 10 billion years. So 10 million years is an instant. So in the life of a galaxy, the birth and death is instantaneous. So anywhere where you see a massive star, that is an active star forming region. So again, they live fast, but beyond that, they're also very hot and very, very bright. And because of that, they're so hot, and they emit ultraviolet light, which is damaging radiation. You know, we wear sunglasses and put on sunscreen for that. It's damaging to just interstellar gas as well. It can break up the gas. If you have a hydrogen atom sitting there, it can just rip that electron right off and ionize that gas, which is, you know, breaking up the atom. Pumps a lot of energy into the gas, and I'll show you some images. And not only that, but once you start forming the massive stars, and they form fast, they almost basically turn off the star formation in the cloud. So you got this big cloud of gas, it's condensing and forming stars, and the first stars you form essentially destroy the cloud. They can also trigger star formation as well. So here I have an image for you of the Rosette Nebula. This is a nearby star forming region in our galaxy, and you can see all these blue stars here are the hot stars. All my students will tell you that hot glowing things glow blue. The cool things are red. All right? It's backwards from your kitchen sink. And all this pink gas, this pink glowing gas that you see, all right, is this stuff, glowing pink. Okay? This is hydrogen. So hydrogen, when you excite it, glows pink like that. So that's what we're seeing is hydrogen. It's the most abundant element in the universe, and it's what stars are made of. And what you can see around the very massive stars that are super hot is there's a hole. All right? There's no longer star formation happening here. You don't see any hydrogen glowing there. You can also see some of the tendrils of dust that blocks our view of the background light. But that hole's not empty. The light from the stars is so energetic that it's breaking up the hydrogen atoms, ionizing it. So now you have ionized gas. The electrons come off, and you just have a naked hydrogen atom there. It's H+. A chemist would call it H+. An astronomer would call it H2. That's Roman numeral 2. So you might hear me slip and call this an H2 region. But you've got ionized gas. You've got a plasma now. And so that does not emit like hydrogen anymore because it's not hydrogen anymore. So, well, it's a proton, but it won't give you those emission lines. So now we have this hole here where the star formation has turned off. But around there, if you search, like in the infrared, for where there are new stars forming, these are low-mass stars forming, as all the shock waves and everything blows out from this central region, it compresses these areas of gas, and you get new stars forming. So it can both turn off and turn on star formation. Because the massive stars are so bright, we can see them very far away. So we can probe star formation in distant galaxies, which is what I do. And again, I've already said that they die young, but they don't just die. They die energetically, very energetically, in supernova explosions. All right? These things are the most gigantic explosions in the universe. And with that, they enrich the interstellar medium with heavy elements. So again, oops, that's better. The universe may have a lot of hydrogen, but of course we're not made of hydrogen. And the carbon in our bodies has to be made in stars. The universe starts with hydrogen and helium, but that's it. All right? The store is empty. You need stars to make all the rest of the stuff. So the fusion in the core of the sun, for example, will eventually, well, it's making more helium now, but it'll eventually make carbon. It might make a little bit of oxygen, but our star is not massive enough to make all the rest of the heavy elements. You need a massive star that can continue to fuse helium and carbon and oxygen, magnesium, all the way up the periodic table to iron. And once you have a core made of iron in a star, it's over. Iron refuses to fuse. If you try to do a fusion reaction with iron, you'll get heavy nickel, which immediately decays right back to iron. So that's it. Once you have that dense core of iron, fusion stops, that core will collapse, and the rest of the star will fall down on top of it. A lot like this. You have the dense iron core in that star, and all the rest of the lighter elements on top of the star. And when that dense core collapses and the rest of the star collapses on top of it, hold on to your coffee, you get a supernova explosion. Now that was supposed, I was aiming for rattan here, so I was supposed to do that. Yes, there you go. That's much more effective. So if anybody was already falling asleep in the first 5 minutes of the talk, it's over now. And this is always armed, so no nodding off. So, so that's where we get iron. I mean, think about that for a minute. The iron in the hemoglobin in your blood was once at the core of a massive star that exploded and spewed its contents through the galaxy. That's where iron comes from, okay? And anything heavier than iron, like gold, comes from the explosion process itself. So what happens during the explosion, the atoms, the nuclei, are force-fed neutrons faster than they can get rid of them, and you just work your way up the periodic table of elements to gold and silver and all the heavier elements, uranium, etc. So massive star formation is important. Its effect on galaxies is really profound. But again, don't forget, it's also immediate. Star formation, massive star formation is instantaneous. All right, so my main area is looking at star-forming galaxies. The Milky Way galaxy that we live in is a star-forming galaxy. We form about one star every year. And starburst galaxies are an unusual breed of otherwise normal galaxies. They're forming a lot of these very massive stars. And all this star formation happens primarily in the nucleus of the galaxy. If you look at our Milky Way, most of the star formation is spread out through the disk, like around where we live. Here, right in the central bulge of the galaxy, in the nucleus, and I'll show you some images, we have all the massive star formation. So that's unusual. To fuel that star formation, the center of the galaxy is full of molecular gas and dust. This is the fuel for building stars. So there's a lot there. That's how I got into this game originally, because I was doing microwave spectroscopy of interstellar gas. So the reason why it's a burst is because if you look at the rate of massive star formation and how much gas is there, there's not enough gas to continue this for forever. Maybe only 100 million years. Now again, I'm throwing around these onlys. But that's brief, okay? The 100 million years is a burst in cosmic time. So the upshot of this is that these things are going to end up being bright, not optically, which we can see in our eyes, but in the radio and in the far infrared. So this is infrared that's just farther from the optical, which we can see with our eyes. And I'll get into all that as we go. I just like to lay some of the stepping stones before we step all over them. So here's my favorite starburst galaxy. It's most people's favorite starburst galaxy, NGC 253. There we go. Also known as the Sculptor Galaxy, because it's in the constellation of Sculptor, or the Silver Dollar Galaxy. And it's a regular spiral galaxy, just like our Milky Way. So our Milky Way galaxy looks like this. It's round, and it's flat. All right, very flat, much flatter than this little model. But the central part, this central red part here in the toy, is the bulge. All right, so it's not flat everywhere. Right in the center, the stellar distribution pops out a little bit in what we call the bulge or the nucleus. And where all the massive star formation is happening, where all the starburst activity is right in the nucleus here. If we zoom in on the nucleus, you'll see this dense concentration of molecular gas. This is a map I made several years ago of the CO emission in the center of that galaxy. And so where the where the gray scale here is darker, you see a lot of fuel for star formation, and sure enough, all these little crosses and symbols are infrared and radio hotspots showing the active star-forming regions. And of course, they're well correlated. So that's some of my work. So what? All right. My mom once asked me, what do you do? What do you do every day when you go to work? So for the students in here interested in my answer, what I told my mother as a professional astrophysicist, what do I do every day? I write almost every day. Tons and tons of writing. You're writing proposals to use telescopes, proposals for grants, you're writing papers, you're writing to your colleagues. And every now and then you do get to work with some data, which is pretty fun. But a lot of writing. So writing is important. So what? What good is it? That's the other question I usually get. I'll take a quote, a rather inflammatory quote from the Nobel laureate Richard Feynman, who explained in his own inimitable way why we do this kind of thing, okay? And so, there is a greater purpose to it all right? It's very interesting. We're talking about, if I didn't move you with the whole hemoglobin thing, then it's going to be hard to move you. But, we do this because it's answering some sort of basic fundamental questions of like where we came from. Star formation is our whole human history, the history of the galaxy and the solar system. So that's why we do it. Okay. So from one end of the spectrum to the other, what's that all mean? We're talking about light here. Radio waves, infrared light, it's all light. It's all just photons. And so we always have to back up and do a little bit of introduction of what light is. We get meteorites. We've gone to the moon and brought back kilograms of moon rocks. But other than that, we get precious little other information directly from space besides light. We get tons and tons and tons of light all the time from space, very little of anything else. It's our most direct probe of the universe. So what is light? It's really just energy, all right? But it's moving energy. Anybody note this? Okay, it's light, it's energy on the move, all right? This is the York thing. So I expected a lot more chuckling. Oh, on the move. So what's waving is just electric and magnetic fields. Light is electromagnetic radiation. So if you have a light wave, it looks like this. It looks like a wave. And what's going on is the electric field's going up and down. And at the same time, we have magnetic fields going side to side. So electricity and magnetism are always together. And it's a waving electric and magnetic field. So we characterize light by its wave properties. We can measure the distance between the wave peaks. It's known as the wavelength. We could count how many wave peaks pass us every second. That's the frequency. So take a look at this. If we look at this wave and we compare it to a wave that, say, has a shorter wavelength, so we'd see a wave like this. Would a wave like this have a higher or lower frequency? You're counting the number of peaks per second passing you. Yeah, higher, all right? So when the wavelength is big, the frequency is low. When the wavelength is short, the frequency is high. And all light, regardless of wavelength or frequency or energy, all light is moving at the speed of light. Radio moves at the speed of light. Infrared moves at the speed of light. It all moves at the speed of light, which is pretty darn fast. But a testament to the vastness of space, it still takes over 8 minutes for sunlight to reach the Earth. Right? The sun's pretty far away. So the different kinds of light have different wave properties. They have different wavelengths and energies. And longer wavelength light has lower energy and a lower frequency. So now let's take a look at the electromagnetic spectrum then. From radio all the way up to gamma rays, hopefully this is more or less visible, we're usually familiar with just this one teeny tiny part of the spectrum. This is the visible spectrum, what we can see with our eyes. But there's so much else there, infrared, ultraviolet, all this other stuff. And we learn a lot from going beyond just the visible. So the radio is this end of the spectrum. It's the lowest end of the spectrum, the lowest energy, the longest wavelength, the lowest frequency light. And the gamma rays are on the other end of the spectrum. High energy, high frequency, very short wavelength. Clicky. Okay, so what do we learn by going to these other wavelengths? Anybody that's ever been to my office knows this poster. This is the multi-wavelength view of the galaxy. This is our own Milky Way galaxy that we're looking at. We live inside this galaxy. So here's the galaxy. It turns around, and we live inside in the sun, around the sun right here. And so from our point of view, when we look out of the plane of the galaxy, we don't see a heck of a lot. When we look below the plane, we don't see much. But when we look around inside the plane of the galaxy, that's where we see all the action. We see all the stars and gas and dust and all that stuff. So when we look around in the sky, the galaxy shows up primarily as a thin strip in the sky like that. Okay? And you can see this at night from a dark location. You'll see that dark band of stars going over. First person to posit that that meant that the galaxy was a disk shape was actually a philosopher, Immanuel Kant. And a long time ago, way before it was ever measured. So let's take a look at a massive star formation tracer, which in this case, I'm starting with the long wavelength radio emission. So what do we see in the radio? This is closely tied to where all the new stars are being formed because you can see it's confined to the disk. Okay? We see that nice flat disk when we're looking at it, and so that's tracing where the stars are forming. But what causes the radio emission? This comes from the supernova explosions. You get a big explosion, it accelerates any electrons that are sitting around, get accelerated up to really high speeds, almost the speed of light. So they're these very high energy electrons, and we just call them, any of these high energy particles, electrons, whatever, we just lump them all into one bucket and call them cosmic rays. They're these very high energy rays, these particles, from the cosmos. So that's it, they're cosmic rays. And cosmic ray emission gives rise to this, to the radio light that we see. When cosmic rays spread out through the galaxy and interact with the galaxy's magnetic field, they give off light. And that light, it's called synchrotron radiation, I'll explain it more in a bit, shows up in the long wavelength radio. And so it's tightly correlated with the star formation because we know it comes from these supernova explosions. The higher frequency radio light also looks like a star formation tracer because it looks just like the radio. The molecular gas also, right along the thin disk, the infrared, these two infrared bands also, closely tied to the thin disk and to star formation. The higher frequency radio light comes from a different process. It's still coming from electrons, but not from cosmic ray electrons. A totally different population of electrons. Remember in the rosette, I showed you that hole, which I called an H2 region. So you've got ionized gas there, and those hot electrons will emit when they interact with protons. So the synchrotron radiation comes from those cosmic rays. They have a very different distribution of energies. You have a lot of cosmic rays at low energy, and then you have this really long tail of high energy cosmic rays. All right? The distribution we call a power law, and I'll show you what that looks like too. But around the H2 regions, seen at the high frequency radio, here the distribution of energies is totally different. It looks like a bell curve. Here you just have hot gas that's been heated by those stars, and so you get a lot of electrons at one particular set of speeds, and then very few very fast electrons, very few really slow electrons. And this is the way a physicist measures temperature. If that distribution is broad, it's hot. If that distribution is narrow, then it's cool. All right? And so this is just emission from hot electrons. We call it thermal emission. Up here, those cosmic rays have a very different distribution of energies, power law distribution, non-thermal. All right? As simple as that. Astronomers keep it simple. It's non-thermal or thermal. So this one's much more closely tied to those hot stars, so it's much more confined to the plane. Whereas these guys, which are zipping along at almost the speed of light, can puff out and get pretty far from the centers of star formation. Plus, they're blasted out by the supernova, too. The molecular gas, this again is the fuel for star formation, so it's tightly constrained to the disk. The infrared emission is coming from dust that's been heated by the stars, and then it glows. So that's tightly confined to the disk and the gas as well. And then the mid-infrared emission here is just even hotter dust. So it's more tightly confined to the star-forming regions. All right, so all these things with check marks show us where the massive star formation is visible or apparent at these different wavelengths. So how about these other ones, including the gamma rays? So let's look in the near-infrared. This is a bit like that old Sesame Street game, right? Some of these things belong together. Some of these are kind of the same, or are they different? All right, so looking at the near-infrared, does this look like a good tracer of massive star formation to you? Just trying to match up the plots. Yes or no? What do you think? My students could tell you I don't ask rhetorical questions. So, yeah, why yeah? I heard one vote for yeah.
I said yeah because it looks like there's a lot of stars, a lot of things going on right there in the center. So.
Right in the center? And is that what we saw in the near infrared or the mid infrared?
I mean, there's still a lot going on there, but
This is the big thing, Miguel. I'm glad you brought it up because here we're seeing this big, this is the galactic bulge. This is the center distribution of stars which sticks up above and below the plane, which we don't see as a massive star formation tracer. In fact, in the near infrared, what we're seeing primarily are old stars. These are cool stars. And so they're good for a lot of different things, but not for tracing star formation, because these are old, low mass, cool stars. Their evolution's very, very slow. So they form and they live almost forever, many trillions of years. But they're the most common type of star in the galaxy. So they dominate the mass of the galaxy, and they let us know where all the structures, the main structures are. But especially looking at that central bulge there, this is an old population. It's not showing us where the new stars are, which is really tightly confined to the disk. In the optical, it gets worse. It's dominated by the bulge, but also look at all these shadows here, right? This is dust. This is foreground dust that's just actually getting in the way. We can't see it. The foreground dust itself emits in the infrared, but here it's just in the way. All right, so the optical stinks. Sorry. That's usually more effective when there are optical astronomers in the room and they all go, hey, you know, but because the radio people think optical is dumb. So then the X-rays, again, have that similar problem. You've got the what we call extinction. It's just this shadowing from the dust. All right, so they don't trace massive star formation very well. So what about the gamma rays, though? So we've gone from one end of the spectrum to the other. What do the gamma rays look like to you? Do they look like they trace the old stellar population or the new stellar, the young stellar population? The young stellar population, yes. Gamma rays are a massive star formation tracer. Much more tightly confined to the disk. You don't see that bulge component. And it looks really a lot like the molecular gas and the radio. And that's because they're tightly coupled together. So these will end up still being useful, as I'll show, but in sort of an indirect way. All right, so let's take a look at the spectrum of a galaxy now. This is NGC 253 again. And here's the different parts of the overall spectrum, the radio part, the infrared, the optical, the X-rays. And this is a really raw data dump. So this isn't really all the data on 253 that's out there, nor is it well organized. But it shows the very basic spectral components. This is showing brightness or flux as a function of frequency or energy. Okay? And this is actually on log scales. So every tick is a factor of 10. So here we've got 100 million hertz, a billion hertz, 10 billion hertz. It goes up by a factor of 10 every time. And then more importantly, the flux scale is also logarithmic. So down here, these radio points are 1, 2, 3 times, all right, 10. It's 1,000 times lower than the infrared peak. All right, so the infrared dominates the spectrum of this galaxy. If you could look at NGC 253 with eyes that were sensitive to every wavelength, you would just see infrared, because it's 1,000 times brighter in the infrared than most of the other parts of the spectrum. So it's a very infrared, bright galaxy. So that's an important point that I'll stress a number of times here. So let's just look at the different parts of the spectrum and reiterate what the sources of the radiation are. So in the far radio here, the low frequency radio, we get supernova cosmic rays generating the radio emission. So you got a supernova explosion, makes all these cosmic rays, and then they radiate this, what I called synchrotron radiation. So this again is the cosmic rays interacting with the magnetic field of the galaxy. So let me show you how that happens. All right, so I got a demo up front here. In this tube, some of you may be able to see a little faint green glow. I'm hopeful. It's a little bit faint. Let me crank it up a little. All right, so in that tube there, there's just mercury gas. And there's an electron beam running through that tube. So there's electrons just blasting through there. And every time an electron hits a mercury atom, it makes the atom glow. So the glowing mercury is tracing out the electron beam. Right now, there's no magnetic field on in there. But when I turn on the magnetic field will point towards and away from you guys. Right? And when I do that, what you'll see is the beam, the electrons will be diverted. Okay? When you turn on the magnetic field, the electron wants to curl around the magnetic field. The magnetic field's pointing out like this, and the electron likes to go around it. That's what it does. And I can even make it, if I really crank up the magnetic field, it does a tight little circle. Now, if that's with the electron just going completely perpendicular to the magnetic field, if it's moving at all along the magnetic field, then it traces out a little spiral, okay, which some of you up close might be able to see. Traces out a little spiral pattern. All right? So this is what charges do in the presence of a magnetic field, especially a light charge like an electron. It goes spiraling around the magnetic field. So the magnetic fields are like this, and it just goes bzz, 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 bzz. Now, anytime you accelerate a charge, to a physicist that means slowing down, speeding up, or changing the direction of a charge, it's going to radiate. So forcing an electron to go around in a circle is going to cause it to radiate. And unlike these electrons, the cosmic ray electrons that supernova create are going at such high speeds that they have a very special kind of spectrum that they emit that we call synchrotron radiation. Remember, the distribution of energies of the cosmic rays is that power law. And so we get a power law spectrum, which looks like a straight line on this plot. All right, so again, just very characteristic. I keep throwing out terms like power law and stuff like that. All you got to know is, it looks like a straight line. So you can recognize that when it pops up again. The higher frequency radio emission, again, I said this was coming from those H2 regions, just like we saw the hole in the Rosette Nebula. What's going on here is, again, we have electrons interacting now with protons. So electrons and protons have different charges, so they're attracted to each other. And so as an electron goes past a proton, the proton says, hey, come on back. And it pulls back the electron and also diverts it a little bit. So instead of going off in a straight line, it kind of curves a little. And also it puts the brakes on the electron. It slows it down. And so anytime you slow down or change the direction of a charge, it radiates. That radiation, we, for some reason, use the German term Bremsstrahlung, which just means braking radiation. All right? So the proton slows down the electron, and that gives off braking radiation, like your brakes squealing. It's like braking radiation. So we call it Bremsstrahlung. Strahlung means radiation, so I'm always very careful not to say Bremsstrahlung radiation, because that's like using your PIN number at the ATM machine. I'm glad some people get that. All right, so when we move to the infrared, again, this is from the dust. You get dust heated by those hot stars. You also get interstellar medium lines, ISM lines, atomic and molecular lines, emission. In the near and mid-infrared, you get a really complicated spectrum that I just cartooned up here like a squiggle. You get mostly emission from very hot dust and small, small dust grains. And these dust grains are so small that some people might just call them molecules, big molecules. They're hundreds or thousands of atoms, so they're really small. They're composed primarily of these things that we call PAHs. They're polycyclic aromatic hydrocarbons, which basically just means they have rings in them. And so they give rise to some of this, and I'm not going to talk about them much more. In the optical, we see stars and nebulae. And then in the X-ray and the high energies, we get these. I know 3 points doesn't look like a straight line, but believe me, the full spectrum does. We get power law emission again. So this is obviously coming from those cosmic ray electrons that were accelerated by supernova explosions, but now they're coming not from synchrotron radiation, but from something else, which gives us very high energy emission. This turns out to be a process called inverse Compton scattering. You have an electron that has a lot of energy, and it bangs into a photon. Well, what photon is it going to bang into? Very likely one of these infrared photons, because there's so many of them. The spectrum's dominated by it. So you have a low energy infrared photon just sitting there minding its own business, and all of a sudden, boom, this cosmic ray electron nails it, and pow, gives it a lot of energy, and now it's an X-ray. Okay? And the cosmic ray basically loses all of its energy to that reaction. So that's known as inverse Compton scattering, where you upscatter photons to very high energies. Very common thing. But notice the source is a cosmic ray, and in the radio, the source is cosmic rays as well, from supernova explosions due to star formation, which is the same process that heated up the dust here. So it's all related. Plus, we're scattering off that infrared emission. So from one end of the spectrum, massive star formation ties together the entire thing. Okay, now in between, I don't want to belittle the near-infrared and the optical and stuff, but they do give us some information. When we look at NGC 253 in the near-infrared, for example, we're seeing all the stellar mass. So this is where we see the cool spiral arms and the nuclear bulge. There's actually a bar in the center there too. But in the optical and the UV, we don't really see much of the starburst. It doesn't stand out, especially the UV. There's so much dust blocking the center there that you just don't get the whole picture in the UV. But it turns out that these bands are useful in one way for studying starbursts, sort of their overall energetics. If we greatly overexpose the ultraviolet, this is what we see. The disk is way saturated, but now look, you see this very faint emission going above and below the plane of the galaxy. So there's gas being blown out above and below the plane by the starburst. All right? The starburst is ejecting material. And we see it in the optical also. This is hydrogen emission. All right? It's this. So there's hydrogen gas out there as well that's glowing. And we see that in the X-ray as well. So here's the center of the galaxy, and here's this X-ray emission coming out the top and the bottom of the galaxy. This is caused by winds from the starburst. All right, so that's supernova explosions. They're just blasting out the center of the galaxy. Winds from the hot stars themselves. Their radiation is very powerful. They also have winds that are blowing off the stars. And just in general, those cosmic rays that are zipping around at almost the speed of light, they go traveling through the galaxy as well and can carry material out with them. So since we know supernova generate those cosmic ray electrons that generate radio emission, then the center of these galaxies should show up brightly in the radio. And indeed it does. So here again on the same scales, NGC 253, we see sort of faint radio emission along the disk, but in the center, the nucleus is really, really bright. Lots of supernova explosions going on there, giving rise to lots of radio emission. NGC 253 looks unusual in the radio. Okay? That bright nucleus is outstanding. In the infrared as well, the nucleus is really pronounced, and you can even see that there's dust out here going up above and below the plane. And in fact, the radio and the infrared are very tightly associated with each other. For many thousands of galaxies, we see this tight correlation between the radio and the infrared emission over many, many decades in luminosity as well as flux. So this is the luminosity of the radio emission from the galaxy and the luminosity of the infrared emission from the galaxy. This is the intrinsic brightness of the galaxy. So if you could stand the same distance from every galaxy, this is how bright they would all be. Over here, this is very similar, but this is the flux. This is the observed brightness. So distant galaxies will look fainter. But again, the radio brightness and the infrared brightness are tightly correlated. Now you can see these gray dots are somewhat outliers. These are galaxies that are a little extra radio bright. That's not related to star formation, though. These are unusual galaxies with special activity going on in the nucleus, like a quasar. So if you have a supermassive black hole in the center of a galaxy that's being fed material, it'll shoot jets out the poles, and they're very bright in the radio. So that's not related to star formation. When you just look at star formation, star-forming galaxies, there's this tight correlation, and that's because it's all tied to the massive star formation. Here, infrared and radio images of galaxies look nearly identical. The infrared image looks a lot like the radio image, and again, it's because ultimately we're talking about the same source, massive star formation. Supernova explosions, the hot stars and the supernova explosions. Okay? The radio is a little more puffed out, a little smoother, a little larger, because those high-speed cosmic rays get a little farther than the warmth from the stars can heat the dust. Now, what about the gamma rays? How do we round out the whole spectrum? So what we're talking about here is gamma rays from regular old galaxies. A lot of the gamma ray community actually studies those quasars, because they're really bright in the gamma rays too. But we're interested in star formation from a normal galaxy. A lot of those guys say that that's foreground contamination. We're looking at the Milky Way, which glows in the gamma ray, and it's just in the way of all those interesting galaxies out there. But I'm interested in the really faint normal galaxies that are out there. So first, let's look at the Milky Way's gamma ray spectrum. All right, so this, again, this is just brightness as a function of frequency or energy. And you can see the Milky Way spectrum, which is all those little plus signs, looks very much like a power law. Okay? All the gamma rays are coming from cosmic ray interactions, which have a power law spectrum. And, okay, so interactions between cosmic rays and interstellar gas and radiation. And the processes, again, are inverse Compton scattering. That gives us sort of a low end of the emission. So you have a cosmic ray electron, hits a photon and shoots it up to gamma ray energies. Bremsstrahlung, this is now non-thermal Bremsstrahlung. So you have a cosmic ray electron that encounters a proton and slows down. And it basically loses all of its energy, which just gets chucked out as a gamma ray photon. And so we get that power law again. And then this is a process we didn't talk about yet, but neutral pion decay. So another reaction that can happen is you can have a cosmic ray proton, a really energetic proton, bash into another proton that's just sitting there, like a hydrogen atom in a cloud. And bam, and it destroys it. And the destruction can take several paths. You can ionize that atom, and that will take away a lot of energy. Or you can start a particle cascade of nuclear reactions that can result in, among other things, particles called pions. Pions can be charged, positive or negative, and they can be neutral, no charge. And a neutral pion will decay almost instantly. And this really is instantly. This is 10 to the minus 13 seconds. Okay? So neutral pions decay instantly into 2 gamma rays. And so that's why we get a bump here. We get a little peak in the spectrum. There's a couple of things. For the most part, it looks like a power law because of the power law spectrum of the protons. But also, there's a certain threshold energy to just run that reaction. So you have to get above that energy. So the power law kind of dies out at lower energies. So if you see this so-called pion bump, or that little shoulder in the spectrum, that's indicative of those proton-proton reactions. So in starburst galaxies, we had predicted that they should be bright in the gamma ray because they have enhancements in all 3 of those reactions. You should see more inverse Compton scattering because they have a lot of infrared photons to scatter off of. There should be more Bremsstrahlung emission because you just got a lot more cosmic rays because there's a lot more supernova explosions. And there should be more neutral pion decay because not only do you have more cosmic rays, but you get a lot more gas. And you remember that map that I had made that I showed you of NGC 253 that had that deep reservoir of molecular gas in the center. So we should get lots. All right, so back in the day, we tried looking for these. That's a little better. We tried looking for these with the original gamma ray telescope, which was called the Compton Gamma Ray Observatory. At the time, it was the most massive thing that the space shuttle ever put into orbit. It was the size of a bus and weighed like 10 buses. And the instrument that I used on it was called EGRET, the Energetic Gamma Ray Experiment Telescope. And so we did some studies back then, and actually these guys later on literally duplicated our study. It's too bad I wasn't the referee. And this was our result. We got nothing, all right? So there were only upper limits. EGRET wasn't sensitive enough to see these faint objects. And, well, so these are all the sensitive detection, upper limits, no detections. This is NGC 253, another bright starburst M82, and then we looked at a whole bunch of starburst galaxies and added them all together, and even then, we didn't have the sensitivity to detect it. So no data never stops anybody, all right? So I spent another 1.5 years of my graduate school career in creating these models that were predictions of the expected gamma ray emission from galaxies. And so no data never stopped anybody. I take a quote from Mark Twain on this. He said, "There is something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact." And that's exactly true in this case. But then the Fermi Gamma Ray Space Telescope was launched, and now we actually have some real data to talk about, which is very exciting. So here's the Fermi image of the gamma ray sky, again dominated by the Milky Way, after just a couple of months. This is actually far more sensitive than EGRET's all-sky map after a few years. So really much, much more sensitive than EGRET was. We see all the familiar features dominated by the Milky Way emission, and we see some of the weird gamma ray things that we see, like quasars. And pulsars also show up, rapidly spinning neutron stars. So again, way better than egret was. We get much better sensitivity, and we can make much finer detailed pictures. That's what the resolution means. It also fills a gap in our our gamma ray window that we had for a while. Ground-based telescopes, since egret was splashed down in 2001, there was this big gap where we didn't have any gamma ray observatories running. But on the ground, they developed this new technique for observing very, very high energy gamma rays. But there was still this gap, but Fermi filled that gap now. And there was a lot of interim studies that were very useful, and some good laboratory work to improve the pion production pipeline, and some other things that made it easier to model. So I improved all of my models and started preparing for the Fermi data launch. And then assisting me on this was a York College physics student who just graduated last year, Nicholas Hunt Walker. He did some of the modeling, but his big contributions was once the first year catalog came out from Fermi last January, he did the lion's share of the work of really figuring out how, once we download the data, how you're supposed to really run the pipeline, reduce the data, and analyze it. It was really incredibly difficult. Working on these high energy missions is a gigantic pain. It's very non-intuitive, really very challenging. Fermi goes around the Earth, every hour and a half or so, and it makes a scan pointing to the North Pole, and then it flips over and it makes a scan pointing to the South Pole, and it has an enormous field of view. So you're scanning your source almost all the time. And so there's all this careful timing and complex stuff you got to do. What a pain. I mean, we were banging our heads against the wall for months till we finally started to generate spectra that we believed and we thought we understood all the systematics and the error bars. Really, really challenging work. Nick is now, I'm happy to say, in the astrophysics PhD program at the University of Washington, one of the best in the country, but he was also accepted to Arizona, Wisconsin, and Columbia. Those are 4 of the best astrophysics programs really in the world. So our York graduates doing us proud. So starbursts were finally detected now, but scoop of all scoops, by the ground-based telescopes. Just before the Fermi catalog came out. And you know who was the referee on that report? Yeah, that was me. I was so honored to get, science calling me and asking me to be a referee. And I was like, oh, wow, that's great. Science wants me to be the referee. And then I read the title, First Detection of Gamma Rays from a Starburst Galaxy. And I was like, oh, frickety, I couldn't believe it. Just wait a few more months, So, well, there you go. But they were also detected by Fermi. So here's M82 and NGC 253, 2 of the brightest starburst galaxies. These were the number 1 and 2 targets. And the Fermi team published these results. You can still see in some energy bins there's still some upper limits, but that's okay. At least there's some data now. Before we had nothing. Underneath the data points, you can see some models just for comparison. They're not fits to the data. They're just for comparison. And the red dotted line here, you'll see, are my models. And the Blom et al., that was also my model. Now I had redone all the models. And this is only after about 10 months of data. And now I have a new spectrum you'll see is much more sensitive with over 2 years of data now all put together. Among the starburst galaxies, some other normal galaxies were detected, like the Large and Small Magellanic Clouds. These are our nearest neighbors. And another mystery source, NGC 4945, which I'll tell you about at the end. So how do the models work? This is the theoretical models. They're computer simulations on the expected gamma ray emission from starburst galaxies. So we want to run the whole pipeline from generating cosmic rays to giving us gamma rays and radio emission and all the other emissions. So where do you think we start to generate the cosmic rays? If you don't know this by now, where do they start? Where do you get the cosmic rays? Supernovas, right. So you get a supernova explosion, and that generates your initial cosmic rays. You got your electrons spiraling out, protons spiraling out in the opposite direction because they're opposite charges. And then what we start with is what I always refer to as an injection spectrum. So there's your power law, injection spectrum, that now meets the interstellar medium. It's a little faint, but that's a cloud. Okay? So those protons and electrons will hit atoms in there and ionize the atoms, losing energy. They'll interact with the magnetic field and give you synchrotron radiation, losing energy. They'll interact with the radiation field, upscattering photons via inverse Compton scattering, losing energy. They'll leave. They'll escape, losing, that energy. And also they'll generate those secondary particles like pions, the neutral pions. Also, charged pions will quickly decay to electrons, which will also give you synchrotron radiation and other things. And it's still a power law, but it has that pion bump in it. So we get a little bit more of a bumpy spectrum, that pion bump, not only from the pions, but from the secondary electrons. So there's a lot going on, but that's the major process. So the result is that we put in this injection spectrum, and what we get out is a steady state spectrum that's significantly altered. At the lowest energies, you see it kind of flattens. And that's mostly from the ionization reactions. So the higher the density of the gas, the more flattening you get. And then up at high energies, it steepens. You lose cosmic rays up at high energies because of all these other interactions. Primarily, the synchrotron is very sensitive to energy. So the very energetic electrons will lose a lot more energy. All right, so this is the result. This is the radio data shown in blue and the gamma ray data for NGC 253 shown in blue. So this is my spectrum of NGC 253 from Fermi. And you can see, so it's better than that original publication now because it has much more data in it, 2 years worth of data. And it's kind of fresh. I literally made this spectrum a couple of weeks ago. And underlying that are some models, are my model fits to the data. And this is a simultaneous fit in the radio as well as in the gamma rays. Okay? And that's pretty close. Believe it or not, this is not too bad of a fit. You might be looking at it like, whoa. But it's actually, that's pretty good. And so there's a few things to notice. I've only just, like I said, started analyzing this. I'm still working on some of the binning and stuff up here to reduce my error bars. But the data are what they are. So there's a couple of things to notice. For one, we definitely now see the pion bump out here. There's a real signature of the pion bump. It was never seen before, even in the first detection. So that's a really big deal for us. We're very excited about it. The results indicate that that these cosmic rays are interacting with a kind of a low density medium. That's a bit surprising. If we break up the models down here, here's the contribution from inverse Compton scattering, from Bremsstrahlung, and the important one is the neutral pion decay. If we increase the density from this black line to the red line, you'll see that the pi 0 decay increases a lot. This is just increasing by a factor of 10, and so we get about a factor of several increase in the expected gamma ray flux. To fit the data, the actual gamma ray observations, requires lower densities. And that's a little bit surprising, and here's why. If we look at the synchrotron emission in the radio, going from the black curve again to the red curve, we're increasing density by a factor of 10. And look what happens when we increase the density. Again, we get more of those ionization losses, and so the spectrum flattens out at low energies. And so we see a much more curved spectrum at high densities than at low densities. And notice that the radio points look more curved than the best fit model. So the radio points seem to indicate high densities, but the gamma ray points seem to indicate low densities. And from my own measurements of the gas in the galaxy, I like high densities too. So it seems like the cosmic rays that are giving rise to the gamma ray emission might be a select population that are interacting very, I don't know, briefly perhaps with the interstellar medium. But if we knew all the answers, it wouldn't be fun. So this is interesting. But I've been waiting years for that spectrum. So it's really, really very satisfying finally at all this time. Okay, then there's NGC 4945. Now I knew 253 and M82 would be the big targets, and I wouldn't beat the Fermi team to the publication punch. But I thought I had a chance with 4945. I was wrong. They just published it a couple months ago. But they did a bad job. So the thing with NGC 4945, it's not just a starburst. It has one of these like little quasar-y things in the center with a jet. So we don't know if the gamma rays are coming from the starburst or from that active nucleus. It did show up in the first Fermi catalog, so it's definitely a gamma ray source, but we don't know what the source is. So here's our spectrum. Nick and I made this spectrum here, the black data points and error bars. The straight line I just put in there as a by-eye fit to the data. The curved lines are my starburst models. Clearly, the starburst is not responsible for all of the gamma ray emission in this galaxy. In fact, we don't see any signature of a pion bump. Here's the pion bump. We don't see that in 4945. What we see is basically a straight, boring power law. That says that the jet is the source of the gamma ray emission. And my colleague that's working with me on this, he and I went to grad school together. And it was funny when I first called him up about his jet models for gamma rays. He was like, oh, so after 25 years, you finally want to work together? So it was pretty cool, though. He took a look at this spectrum. He looked at the radio, and he said, that radio jet will not give you these gamma rays. Again, from one end of the spectrum to the other, whether it's a starburst or this active galactic nucleus, this part of the spectrum of 4945, we don't get yet. It's still a mystery, but we can at least estimate what the contribution of the starburst is to the high energy emission. But really, it's some combination of the AGN and the starburst, and it's still kind of mysterious. But that first detection paper that came out a couple months ago on 4945 said, oh, it's a starburst. But that's because they don't have the models that show that it's not. So once we figure this out, that'll be pretty satisfying. All right, so from one end of the spectrum to the other, star formation is the link, and cosmic rays are the vehicle. So in the middle there, the optical and the UV, they don't really probe directly the starburst because dust gets in the way, but they do give us an idea of the overall energetics because we see the winds show up in those tracers. The radio is the direct probe of those cosmic ray electrons that are accelerated by supernova explosions from the massive star-forming regions, and as well the high-frequency radio you get from those H2 regions, the cooked gas right around those hot stars. And then the far-infrared light, which dominates the spectrum of the galaxy, again comes from the same source, the massive stars that are heating the dust, which then radiate in the infrared. The gamma rays depend on all of that. They depend on the cosmic rays, they depend on the interaction with the gas, they depend on the interaction with the radiation field, everything. All right? So to analyze the gamma ray emission from a starburst galaxy, you have to actually look at the entire spectrum from one end to the other. So that's it. Thank you very much. Now I will take your abuse.
I wanted to ask about some of the times that you mentioned, something that happens in 10 to the minus 13 seconds. How can we measure something so tiny?
That's a really good question. And honestly, I don't... Where did Kevin go? Oh, do you know how those decay rates, how those incredibly fast decay rates, because this was before the super high-speed probes were done. I know that 10 to the minus 13 seconds, that is the well-known decay rate for a neutral pion. Do you know how those are measured in the lab?
Yes, it's a long story, but it has to do with the, you measure something that's called the decay width. So you look at the actual energies of the decaying particles, and because of quantum mechanics, they're not exactly what special relativity tells you they will be. They're broadened a little bit, and the amount of the shorter the time period over which the decay happens, the broader this curve is. So you go into the laboratory and you measure the decay rate or the decays of a very large number of pions, and you plot out the spectrum of their final product energies, and then you just measure the width of the distribution you get. And 1 over that is the lifetime.
Farley, they're Fourier conjugates, so when you have a broad width in one component, it means it's narrow in the other. So that's where it comes from. So he's a mathematician, so I can throw a Fourier at him. Dan?
2 things. One is, so most of the argon, which I think from your point of view is a heavy element, on the Earth.
Yeah, everything heavier than helium, astronomers call a metal.
Right. So that metal is generated primarily on the Earth. So it comes from radioactive decay of potassium, right? So he said all of the iron we get comes from supernova explosions, but isn't some of it from radioactive decay of heavier elements?
It can be, yeah, but I mean the primary source of iron, if you look at the cosmic abundance of the elements, hydrogen's the most, and then helium, and then it goes down in a bit of a sawtooth pattern just because of the way that the fusion reactions happen. You're basically always adding helium. You're not adding hydrogen to things, so you always go up by even numbers that way. But then you get down to a round iron, and there's a peak. It's the iron peak. So you get a bunch up down there. That's definitely from nucleosynthesis and stellar cores.
Yeah, but that's the, well, okay, anyway, talk about that.
Yeah.
The other thing is, sorry, the second question. So I think you made a really interesting point by implication, which is that astronomers are organized by which piece of the spectrum, the electromagnetic spectrum they work in, not by what kinds of phenomena they study or what kinds of stars or something like that.
It is a little typical, yeah.
Explain that a little bit for everybody's benefit. I think it's a really interesting point.
It's even more weird because when I started in astronomy, somebody asked me, "Are you an observer or a theorist or an experimentalist?" And I was like, "Well, don't we kind of do all of it?" And that's in some sense true, but once I became a professional, I realized I was an observer, even though I've done quite a bit of theory. But a theorist is like pencil and paper, an observer is telescopes, and an experimentalist builds stuff. So that's the distinction. So, if you really boil it down, I'm an observer. And then, yeah, observers have sort of a, their speciality. So the telescopes they know how to use. And so it's almost just technologically driven. So and then once you're using those, you understand those sources of that radiation very intimately. So I'm a radio astronomer. I'm also a gamma ray astronomer, sort of. I still think of myself as a radio astronomer. But yeah, people break it down that way. And if you started off with a scientific interest, like my original interest was the interstellar medium. Well, that made me a radio astronomer, because that's the way you study the interstellar medium, is in the radio. So if you're interested in cool stars, well, that makes you an infrared astronomer, because that's the way you study cool stars. And so stuff like that. So I guess that's the way it happens. If you're interested in active galaxies, quasars, stuff like that, you could work the high energy or the low energy, because they're bright in the radio as well as the X-ray and the gamma ray. So I'm the weirdo that does star formation up at the gamma rays. There aren't too many of us that do that. It's the only way I can publish, because it's hard to be competitive.
From what you said, we live in a solar system, a star system, and we have all of these heavy elements, to uranium.
Mm-hmm.
And so we can conclude then that all of us, the world around us, are the products of a supernova.
Yeah.
The matter we're made of must have once been involved in that.
Yes.
Supernova.
Yeah, it's the only way to get that stuff. Yeah, you can't make gold in the center of a star. You have to blow up a star to make the gold. And the sun. Yeah, the sun is definitely a second generation star. So like the stars in the bulge are really an early generation star. They have very low metallicity, very few metals. Their iron content is low, for example. And the sun is rich in metals. It's got sodium, it has magnesium, stuff like that. So yeah, you don't get that stuff unless the cloud you formed from had been seeded by that first generation or so of stars. Yeah. I mean, the sun's only 4.5 billion years old, and the galaxy is more like 12 billion years old. The stars in the disk are like 10 billion years old. So, definitely a second generation.
I just want to follow up on what Stan said. I can remember Carl Sagan saying, "We are all star stuff."
Yeah. Right. I left my suede patches. So.
Yeah, we both said we are the stuff that we
There's nothing but stardust. Why are all the galaxies flat?
They're not all flat. A lot of them look like a galactic bulge. A lot of them have just sort of a ellipsoidal shape. In fact, most of them do. The flat ones have a significant rotation, which is what actually flattens them out. So the ones that have a more complex rotation or complex stellar motions are elliptical galaxies. These are spiral galaxies. So it's a mixed bag out there of spirals and ellipticals. The interesting thing about spirals is they have all the gas. Elliptical galaxies are just all old stars. There's no gas and dust, so you don't get any new stars there. Spiral galaxies have the star formation. So I personally never look at elliptical galaxies. They got nothing new going on.
I never did the math, but is the 675 million miles per hour the conversion to the 3.0 times 10 to the 8?
Yes. Yes, unless I screwed it up, which I don't think I did.
To piggyback on
yeah, 300,000 kilometers per second is the speed of light.
How do you actually measure how do you measure light in that sense?
How do you measure like the speed of light?
Yeah.
Well, there's a famous experiment. Galileo did the first attempted measurement of the speed of light. You know, two guys on a hill with a lantern, and he'd say, "Go!" You know, and they would say, well, it was instantaneous. But he actually rightly concluded that it was either instantaneous or very, very fast. So he was the first astronomer to try to measure the speed of light. The first person to really measure the speed of light was Romer, who looked at the moons of Jupiter like a clock. They move around just like clockwork. And lo and behold, when Jupiter's farther away from us, the clock runs slow. Not slow, but it's behind. And so he was looking for eclipses of the moons behind Jupiter, and they were always a little late. And then when Jupiter was close to us, the eclipses were always a little early. And so he was able to measure the speed of light that way. And the next astronomer to measure the speed of light was James Bradley in 1726, who was the first person to prove that the Earth moved around the sun, first person to prove that the Earth moved through space, and to confirm that Copernicus was right. And that was a different measurement, which I won't tell you. But nowadays, usually it's using lasers and studying their wavelengths and frequencies in a variety of ways to measure the speed. There was the first really precise measurement was with a rotating toothed mirror that would measure, you know, how quickly the light traveled back and forth between the mirror and the observer and things like that. But it's rather straightforward measurement to measure the speed of light.
Can you talk a little bit about some of the contemporary conversations about discoveries? I'm thinking of the Gliese. Is there anything?
Yeah, Gliese 581 is a planetary system, so there's several planets around it. What happens is you have a planet going around a star, and you can't see the planet because the star is super, super bright. The planet's totally faint. It'd be like, you know, imagine a Mack truck with all of its bright lights on at night, shining right in your face, and I asked you, is the truck driver smiling? Okay? If you look really hard, right, you might be able to tell, but it's basically impossible to see the planet directly. But as the planet goes around the star, all right, I'm glad I happened to bring this today. So the planet's going around the star like that, but notice the way my hand is moving, opposite of the ball. All right? My hand is moving up and down when the ball is moving down and up, sort of in reaction. So as the ball goes around, the planet is also tugging on the star. The planet doesn't just go around the star. The planet and star go around each other. So what you can do is look at the spectrum of the star very, very sensitively and see if it's moving back and forth. And so they look for those signatures. Now, if it has one planet, it'll move back and forth very regularly. If it has two planets, it'll move back and forth not so regularly. If it has three planets, it'll move back and forth harder. So this has something like 5 planets around it. So it has a very complex motion. And one group analyzed a bunch of data and saw a little spike that indicated that there was another planet, and that one happened to be in the habitable zone of the star. Not too close to get baked, not too far away to freeze, but right in the middle where you could have liquid water. So that was an exciting thing. Another group shortly after that did a very similar analysis with a different, more extensive data set from the same instrument and did not see that signal. So the planet kind of disappeared from their data set. But anyway, in time that'll be ironed out whether it's there or not. But this is what scientists do, you know. Somebody makes a measurement, makes an interpretation, and says, look at that. And then another person goes out and, you know, science is out there for the picking. You don't have to take our word for it. If I say this is the speed of light and I told you how to measure it, you know, you go out and you measure it. Everybody can, the secrets of the universe are not secret. They're accessible to anybody with the expertise. So go out and measure it. You don't have to take my word for it. So, you know, There are other people that will tell you things and say, take my word for it. That's not science. So you gotta, you know, if you want to deal with science, you can always go measure it yourself. And so this is what people do. So there was a claim, another group measured it, and right now they don't agree. Nobody says they're wrong. They just say, let's get more, you know, because it's fun.
I know you have an appointment at the Museum of Natural History. Could you describe what you do there?
Yeah, so I'm in the astrophysics department there, and Mandy Holford in chemistry also has an appointment at the museum in their biodiversity area. And so I'm basically a contributing member to the department. I mostly started to go there because they had their weekly seminars, and I could go for an astrophysics seminar. It's also sort of, you know, a nice collegial environment full of astronomers, so we can all have an interesting lunch and things like that. Now there's actually 5 CUNY professors that have associate positions in the department, and then we go with our students too. So now when we have seminars, we take up about half the room. CUNY is a big presence at the museum now, so it's really great. And we're also starting to develop our graduate program, and the idea from the grad center and the museum is that the museum would be their home base. That would be, so you know, there's 7 of us in astrophysics at the university now, but we're scattered all over the place. The museum, and if you will, down the street, the grad center, is sort of our department. You know, if we were at any one place, we would be a department. So that's the way we act as a group and put all of our students together. In terms of what I do for the museum at the museum, I worked on I was the project scientist of the most recent space show, Journey to the Stars. And we just released back on October 10th, for the 10th anniversary of the Rose Center, the new Big Bang show. So there's the big sphere where you can watch the space show. And under that is the bowl, what we call the bowl, that leads you to that spiral path, that spiral pathway. And so when you go in to see the Big Bang show, it's brand new. No more Maya Angelou, sorry. And now it's Liam Neeson is in there. You can hear from Aslan telling you about the beginning of the universe in the bowl. And I worked on that one most recently. That's only 3 minutes, 47 seconds, and you don't have to pay extra for it. But, so that was a bit of a quicker production. But that's some of the stuff that I do at the museum. Yeah. Oh, there's also an REU program, a CUNY AIM&H REU program. So every other summer I take on an REU that's housed at the museum. Sometimes they're from CUNY, sometimes not. Joe?
I can tell him, if you are interested of using the speed of light, we have some equipment.
All right.
Oh, here? Okay.
Yeah, that's right. We do have this setup. You need a really long, a big space to do it right, but because over short spaces it doesn't work, right? I'm looking at you, Dan, because that group at the Source Forge.
Over short distances. Yeah, you just have to be ready to measure the time really precisely.
Right. Their equipment didn't do it.
A foot per nanosecond.
It's fast. It's 30 centimeter gigahertz in my world.
It's the same thing.
Now a round of applause for Kim. For the benefit of either faculty or students who are here for the first time, we've got a couple of traditions in the Provost Lecture Series. One of which is to have a memento of the lecture given to the speakers. And we simply capture in a nice frame poster.
Wow.
Nice picture of the speaker, stars, and give it to that person so he or she can put it wherever he or she feels is appropriate. So congratulations.
Thank you very much.